Today, we will be talking about several aspects or statistics that can be used to describe both nodes within a network and the network as a whole. One of the most intuitive node properties that we might think about calculating is degree. So in a more colloquial sense, degree is simply the number of friends that a particular person might have. In a more technical sense, we might think of this as the number of edges that are incident to a vertex, or the number of links or ties that a particular node has. So in the example network that we see on the screen, A has a tie to nodes B, C, D, E, and F, and that would be a degree of 5. If we look at F then, what would be the degree of F? Yes, that's right. I'm assuming you all guessed that the answer is 1. So we can see that in fact, because this is a star network, a concept that we'll return to later, all 5 of the nodes, B, C, D, E, and F, have a degree of only 1 because they have only one edge that is incident to them, the edge that goes to node A. Now, if we want to think about degree across all of the nodes within a network, then that concept is degree distribution. So the degree distribution is a property of a network and not of a node. A degree distribution then basically tells us how many nodes have 1 friend or even 0 friends, how many have 2, 3, 10, 20 friends. And you can think about this as a nice way to summarize the overall level of activity of all the nodes in a network. And in fact, it can be a nice way to compare networks to one another. So we'll look now at 2 examples of social media networks and the degree distribution in those networks. One that many of you may be familiar with is Facebook friends. Now, personally, I don't find that this degree distribution seems at all like the one that I have seen with among my friends, because here you see that most people on Facebook, at some point at least, the sort of central tendency here is between, say, 17 and 30 friends, and there are fewer and fewer people as you move up to, say, 97 or even 100 friends. At least among my Facebook friends, I find that number is much higher and distributed. Still, though, somewhat, in a sense, normally looking. In this case, the truncation down at 0 means that it's not entirely normal, but this does give you some sense that it's not the case that there are some people that have, thousands and thousands of Facebook friends and others that have only 1. Now, that is not true, though, when we think about Twitter. Twitter has a very different degree distribution than Facebook. Here we can see that almost all Twitter users have at most 0, 1, or maybe 2 people that follow them, whereas there are some Twitter users that have not just 97, but I'm sure that, they're the Kim Kardashians, Kylie Jenners of the world that have millions, and then there are even those that have just a few million, not 40 million, and well-known pundits or even political scientists that might have 500 or 1,000. But most of us don't have that many. We might have 1 or 2 people that that follow us, and ironically, we follow many more people than that. So actually, the degree of Twitter, the people that we follow on Twitter will probably look very different than the degree distribution of people following us. So a topic that you might want to think a little bit about and that we'll be discussing in class or in person and really throughout the term are what types of things might drive degree distribution. Which types of relationships are going to be likely to have a more normal or sort of a more central, a lot of people are going to have around the same number as opposed to those that have a very skewed, a very long right-hand tail. Are there cases where we might see even a bimodal distribution? So think about that, talk about that, because theoretically there are good reasons to think that something about degree distribution is going to tell us a lot about what's going on in a network. Now, in thinking about Twitter and the idea of being followed or following brings us back to the idea that some networks, in fact, are directed, and therefore we can distinguish between in degree, or the number of people who say that I am their friend, from out degree, or the number of people who I say are my friends. So again, back to Twitter, in degree would be the number of people following me, and out degree would be the number of people that I am following on Twitter. Comparing the in degree and out degree distribution may be a good way to think about networks and sort of what types of status dynamics are in play, particularly when there's a big difference between in degree and out degree distribution. Giving a citation, for example, and receiving a citation mean very different things. Now, for an exercise at home, take a look at these pictures and think for a second, what is A's degree? And also, what is B's out degree? Are these things you can calculate easily? So you probably very quickly were able to figure out that A's degree is 7 and B's out degree is 3, because the fourth node that is connected to B is in fact an in degree and not an out degree. So it is not an outgoing link but an incoming link. Why is degree important? As we noted briefly earlier, distribution of degree can tell us a lot about sort of what's going on. What type of relationship are we studying? In general, when you think about weak links, you think about people having lots of those weak links, and perhaps some people having a whole lot more weak links than others. Though that's not always the case. Whereas strong ties that require costly investment, it's harder for some people to have thousands or millions because they simply don't have the time or energy to invest in that many relationships. So Twitter, for example, is this great platform in which you would expect to have a very skewed degree, because every investment of energy, it doesn't matter whether you're sending it to 40 million people or 40 people or 4 people, it's the same investment of energy. So you're able to sustain a much larger network. We're going to come back to these concepts, and particularly things about how degree is related to dynamics of status, judgment, and evaluation under uncertainty, when we come back to the theories of network formation in the week right after spring break. But I think even without having looked at these formal theories, it's pretty intuitive as you think about the types of networks you know in the world, as you think about the way degree might be distributed across these networks, you'll get a nice sense of how some of the theoretical implications of degree and how you might start to form different degree distributions in different types of networks. It's always the case, and we'll come back to this with the concept of degree centrality, that looking at things like in degree and out degree can often be some sort of an indicator of social status or prominence in a network. Now, a closely related concept to degree is the concept of network density. I say closely related because, as we'll see, if you think about an average normalized degree, it's actually the same as network density. But before we get on to the math, what I'd like to do is revisit a concept that you might recognize from your most recent homework syntax file. And that is the idea that there are 3 different types of dyads, at least when we're talking about directed relationships. These are mutual dyads, in which A sends a tie to B and B sends a tie to A. An asymmetric dyad, in which either A or B send a tie to each other, but not vice versa, so this is not a reciprocal relationship. And a null dyad, in which A and B do not send a tie to each other and do not even send a one-way tie. These are the numbers that you got in a dyad census. If you had an undirected network, then you would have either gotten only there is a dyad or there isn't a dyad. You don't get the nuance of either mutual or asymmetric dyads. Now, why does this become quite important? Because it helps us then calculate in a pretty straightforward fashion network density, or the general level of linkage in a network. What you're aiming for in a measure of network density is to come up with, out of all the ties that could be in a network, if it were fully connected or complete, right, which is a concept we learned last week, then what proportion of all the ties that could exist actually exist? That's going to be our concept of density. Why do we want to have it as a proportion? Because that will allow density to range between 0 and 1, which is always a good thing when you're dealing with statistics. And so the density of a whole network then is going to simply be a normalized average degree. Now, we can see in our mathematical notation that, in essence, what you want to do whenever you're calculating possible ties is it's slightly different depending on whether it's a directed or undirected network. You, in essence, have to divide the whole thing by 2 if you're dealing with undirected ties. And to calculate actual ties, we get this nice idea that you can do 2 times the number of mutual dyads plus sort of only 1 times the number of asymmetric dyads, and then you divide this by your possible ties, which is what's very nice about the dyad census that we had you run, is it's a nice way to calculate density. Now, let's then see if we can actually put this into action with our toy networks. Let's look at the one on both the left and the right and see if you can calculate what the density is of both of these networks. Now, some of you may recognize that on the left, we have a complete network. Therefore, we would hope at least, right, that this network would have a density of 1. And sure enough, if we go through how many links between these 4 nodes are possible, it's going to be 4 times 4 minus 1 divided by 2 because we're dealing with undirected links. So that number is 6. Sure enough, we see actually that there are 6 links, so our density is 1. Now, if we look on the right, what we could see is that 2 of those links are missing. So we should see a density of less than 1, which is exactly what we see. We see that only 4 of the links out of the 6 possible are there. Therefore, our density is 0.667, or 67% of all the ties that could be in the network are in the one that we actually observe. Now, those are toy examples, so let me show you what a slightly more realistic example of the difference between low and high density look like. These are published networks. You can see that even though they both look a lot like hairballs, the one on the left is a much relatively lower density than the one on the right. I'll also draw your attention to the fact that with the exception of 3 isolates that are up to the upper left-hand corner, you can see that in both of the 2 networks, even though the one on the left is lower density, you still have a giant component that comprises most of the nodes in the network, or in other words, a connected network in both cases. So even though density does, as the density goes down, you're losing 3 of the isolates, in general, you aren't losing the idea that you have a connected component. That is not the case, though, when we turn to a different type of real-world network data. This is NGO, network density, between human rights organizations and development NGOs. Here you can see that in the development world, it's often the case that NGOs simply do not talk to each other. As a result, we have multiple components, 3 larger ones and many smaller ones, in this very low-density network. On the other hand, on the left-hand side with the human rights networks, we see higher density network with a single connected component, or what appears to be a single connected component, bringing all the groups together. Now, this should therefore be an indicator of one of the underlying mathematical results we know, which is in general, as density goes down, you're going to tend to see networks that are originally connected actually break apart into multiple components, because as there are fewer and fewer ties present, even in random networks where ties are made completely random, you are going to see less of a chance that all of the nodes can walk. There's a walk available from any node in the network to any other node in the network, or i.e. the network is connected. So this gives us some insight then into why density might be important. Number one, a concept we've talked about before, the idea that when you have higher density networks, you're going to have multiple ways in which information might travel between 2 points. So there could be multiple walks that connect node A and node B. And so if a piece of information or a resource needs to travel there, it's much more likely to do so. You could also think about things like, in general, if people are interacting and quite sociable in a sort of Putnam-esque way, we might think about this being high social capital, and low density might mean low interaction, low social capital. Now, that's not exactly technical, but still it's an evocative idea. In general, though, what we do know more technically is that low density is going to mean much less probability of spread in general, though that's more about the component structure than anything, in the sense that we know that if there are completely disconnected components, an idea or a virus or a resource can't jump from one component to another unless there's some degree of interaction between nodes in the 2 components. And we also know that higher density is less likely to have those types of artificial barriers created by component structure. A concept we'll also return to in the future is that high levels of density or transitivity can actually indicate higher levels of normative constraint. one thing I'd like to flag, again, we'll return to this in the future weeks, is that methodologically, higher density networks can cause issues for estimation, especially when you work with things like ergoms or other types of statistical models. Now, I mentioned the concept of transitivity. There was a transitivity index on your most recent homework. So now I'm going to talk about the concepts of transitivity and clustering coefficient. We've just learned about the concept of density. Another way to think about density would be to think about what are the density of the neighborhood around a central ego or an egocentric network. So in this case, we have Homer Simpson, and we might be interested, how likely are Homer's friends to know each other? This is called the local clustering coefficient, and is more generally thought of as, we're going to see, the clustering coefficient, we'll be talking about an average of the local clustering coefficient. It's a very important concept. So in this case, what we can do is we can say, okay, we see that Homer has 8 friends or nodes that are in the neighborhood immediately surrounding him. With those 8 friends, because these are undirected ties, we can then calculate that there are 28 possible links that could exist between those 8 nodes. But if we go through and sort of count by hand, you can see that there are, in fact, only 9 ties not involving Homer in this little network that appears on the screen. Therefore, the local clustering coefficient in the egocentric network surrounding Homer is about 0.32. Now, let's put that concept aside for a minute and think for a minute instead about the concept of transitivity and triads. So a triad is going to be any 3 nodes in the network plus which ties exist between them. And once we have defined that, once we've defined a triad in that way, we can think about 4 prototypical types of triads, at least in undirected networks, and we'll see that there are variants of these in directed networks. So instead of having our mutual, asymmetric, and null, what we can see is there's the equivalent of a null. It's called an empty triad. It means there's no ties between any of the 3 nodes. There's a one edge, which means that there is a tie between, say, A and B, but not between A and C or B and C. There's a 2 path, which means that you can get from any node in the triad to any other node in the triad, but it's not necessarily a closed triad, as in the case of a triangle, where you see that A is connected to C, C is connected to B, B is connected to A. Now, the real ones to focus on here are the idea of a 2-path and a triangle. So what transitivity is the idea that you actually close up a 2-path. So there will be, again, returning to the concepts of balance theory or pecking orders. Both of these are pulling on ideas of transitivity and how transitivity might exist in a network. But the most important concept here is the difference between a 2-path and a triangle. Now, in your triad census, when you were dealing with directed ties, what you see is that there are actually 16 unique combinations of directed dyadic ties that can exist. And these are all helpfully named by the number of man dyads that exist. So, for example, if you have a 0, 0, 3, it means you have 0 mutual dyads, 0 asymmetric dyads, and 3 null dyads. In addition, there can actually be a direction, like up or down. And so if you contrast 0, 2, 1, D, what that means is that there are outgoing ties from the one node in which and if it's 0, 2, 1 up, it means that both of the things are going into the node that is the focal node that has the 2 asymmetric ties. And the 1 means there's still 1 null. Now, back to our concept of the differences between either closed triplets and those connected triplets, or any set of 3 vertices that are connected by a walk of at least 2, we can now calculate the global clustering coefficient regardless of whether we're talking about directed or undirected networks by taking the number of closed triplets that exist, i.e. the number of triangles in the nomenclature that we saw before, and dividing it by the number of connected triplets, which consists of basically all of the closed triplets and all of the 2 walk or 2-star triplets. In this case, we have the closed triplets indicated in green, and in red we have the 2 star triplets. To actually calculate, though, the correct numbers is a little bit more complicated. You can see here that we have to account for the fact that there's different ways you can have a 120D or a 120U in both the closed and potential. And this is the basic formula you can use. This, though, the reason I want to show you this is because this is the way that in the R software, the transitivity index that you might have seen is calculated. Now, some of you might have noticed that I might have put a note on your homework like, oh, that's strange. The transitivity index is not the same as network density. What do you think's going on? And the reason I would have noted this is because, in general, we believe that the transitivity index in a random network, i.e. one in which there's not some tendency to form communities where people know friends of friends of friends, then the transitivity in that network should be very similar to the density of the network. So when you see very different scores on the transitivity index and overall network density, it means there's something interesting going on in the way your network is formed, that there's some type of greater tendency, for example, to form some sort of a community structure. Now, what you can then see is this global clustering, or more commonly called the transitivity index, is one way to calculate clustering in the network, whereas the local clustering coefficient, where we can take the average of that, or what's often just called the clustering coefficient, is another way we can think about clustering or transitivity in the network, at the network level. The biggest difference between these two measures, because they are not mathematically at all the same measure, is that the transitivity index, or global clustering measure, puts more emphasis on high-degree nodes. So if you have many high-degree nodes, you're really sort of taking those into account because you're counting things multiple times, whereas the average local clustering coefficient will really be sort of, that will be penalized if you have a lot of low-degree nodes involved. Now, when we talked about degree earlier, we mentioned the concept of centrality. So now I'd like to talk to you about the node-level property of centrality and the network measure of centralization. Centrality at some level has a very, well, of course that's what it means, type of meaning. It just means that a node in a graph might be considered more prominent relative to other nodes. So it's if you say someone is very central to a group, maybe it means they have a lot of friends around them, or in some ways they're very prominent. And in fact, what we're going to see is there's lots of different ways to get in and measure in a very specific way what centrality is, even though in a general construct way, the concept of centrality might be used to apply to all the different measures. Centralization, however, is the property of the graph as a whole, not just as a node. So in the images that we have here, you can see that the X-shaped graph is quite centralized. So there's one node in the middle, and then, in fact, to get from the sort of bottom right-hand corner to the top right-hand corner of the X, you have to travel a fairly long path, and you always, no matter what, have to go through this one node in the middle. However, if you compare that to the circle, there you can see that everyone has exactly 2 friends. No matter what, you're having to travel a long way around the circle. So that's going to be a graph where there's not a lot of centralization. Mathematically, what we're going to tend to do is compare, in again, a ratio sense, the actual sum of differences in centrality scores to the maximum possible sum of centrality scores. Now, conceptually, that sounds a little bit fuzzy, so let me give you a clear example. Here's how we're going to calculate centralization. So let's just, for the purposes of this example, assume we're going to give A a score of 5 because that is the number of outgoing and incoming, or just number of ties that A has. And we're going to give B, C, D, E, and F a score of 1. Now, if we look at the differences between A and B, C, D, E, and F, we can see that those sum up to be 20 is the sum. But then if we try to think about what the maximum number or the maximum difference that could exist in the network, a star network is in fact the most centralized network. So in other words, it's a network in which it's connected, but A has every possible tie that could exist, and everybody else has only 1. Nicely enough, what we see is that our centralization score is 1, which again is what it should be. So what we can see is that this particular formula that we have right here means that whenever we calculate a centralization score from any type of centrality score, it will always be between 0 and 1 because of the way we've defined it. It's a very nice property of a centralization score. So it doesn't matter what measure of centrality we put in, we can always calculate centralization in a very much the same way. Now, why are centrality and centralization important? Centrality obviously matters a lot for sort of saying who's important or not important to a network. The concept of centralization really matters a lot for thinking about how information and ideas might flow across a network. Now, to some extent, when you think about highly centralized network, you think about a network in which a few people can control the flow of information. So there's no way, for example, from information back in that star-shaped structure to get from like point C to point F without going through point A. So point A can distort or in some way change the information. However, on the other hand, it's actually quite easy to coordinate. So in fact, a highly centralized network can enable easy coordination because there's one central broadcast point. People have pointed to Twitter as, in essence, a way to replicate having a highly centralized network because it is its own sort of centralized broadcast. So you can actually have a less highly centralized network working with a central broadcasting technology that can really help the ability to coordinate and act together collectively. But in general, we tend to think of networks high in centralization as being, on the one hand, more able to control the flow of information, but on the other hand, more easily able to coordinate. Now, I'll mention that there are multiple ways to calculate centrality. The one that you're going to learn about today, or have in essence already learned about, is degree centrality. But in future weeks, we'll be looking at things like closeness, betweenness, and eigenvector centrality. These are all just slightly different ways to get at the overall construct of centrality, but each is going to have its own theoretical background to explain why this measure is slightly different than the others. Degree centrality is going to be simply proportional to the number of nodes to which a node is linked, so the number of ties that it has. Again, it can be centralized, it can be normalized to go between 0 and 1. You can see here that there are other ways, the closeness between this and power, just to give you some sense of where we're going on the course. But the software will calculate the degree centrality for you. What's really important to realize is that even the 4 that we're going to look at are far from the only measures. There's k-step reach, there's average or separated distance. You can go on and on. I can't tell you how many different centrality measures that exist. Now, the reason that each of these exists is because they all correspond to a slightly different belief about either how networks form or how information or resources spread across a network. So, for right now, you don't really need to worry so much about, should I be using degree centrality or something else? Degree is always a nice place to start. What really matters is as you get a more refined theory about the process that's either contributing to the formation of the network or the process you think is acting on the network, the ways in which people are responding to their context and the dynamic is playing out across the network, then you might be looking for a more refined measure that, say, deals better with valued networks or really looks at the flow of information as opposed to simply prominence in a degree sense. Now, a big caveat, of course, is that different measures are often highly correlated. In fact, in many cases, they don't even seem to exhibit much in the way of discriminant validity. So before you sort of say it's definitely this measure versus that measure, you often want to check a few of them and see how tightly correlated they are in your particular network, because in some networks, they will be more tightly correlated than others. Thanks very much, and we will be discussing more in class.